For this problem, people, what's NM? Gabby? You got 55? Can we get confirmation on the 55?
Yes.
Let's go. What's JLM? Christina?
245.
How'd you get it?
I added 160 plus 65.
Good. We need to go this way, guys. Do you guys see why? Because we have to go from J to L to M. Okay? And L needs to be my middle letter. Do you guys see why we have to go this way? If we went the other way, right? M would be our middle letter. That won't work. Okay? So we have to go this way. And you would add 120 with 60 and 65. And we would get 245. Can I get confirmation on that one?
Yeah.
Awesome. Okay. What was NLK? 180? It was a semicircle, okay? So going from N to L to K creates exactly 180 degrees, semicircle. And then LMN.
120.
You just added 65 and 55, right?
Yeah, it's vertical.
And you got 120. Bingo. We good? Oh, Emma, that's cool. I didn't even notice that. It is vertical to the 120. Do you guys see that?
For the first one, you don't have to subtract all of them from 360. You just do 120 and then subtract
120 minus
65.
65. I didn't even notice that. Did you guys see that?
No.
So the angle that we just found, or the arc that we just found, which was NQL. I'm sorry, I'm saying the angle, the central angle. The arc that we found, which was NL, right? No. LMN. Did we do that wrong?
No.
Okay, little thing, guys, okay? We shouldn't be using an M here. Since it's a minor arc, right? It should just be 2 letters. Yes? Okay? So I'll have to double check that, but I'm pretty sure that was a typo. Okay, it should just be LN. Yes, Christian. It's 11:11. Today, what we are learning is about chords. Okay? So the first thing that I want us to do you guys have this slide on yours?
Yeah.
Okay. Is I want you guys to take a look at this. So the difference between a chord and a semicircle. We already know the difference, right? A chord doesn't necessarily go through the center, right? But a diameter has to go through what point? The center, right? So if you're drawing a chord, you're going to end up with a major arc and a minor arc. But if you draw a diameter, you split your circle into what? 2 semicircles, okay? Now, one thing that I want you guys to do, draw a circle somewhere on your page. A perfect circle. Use Notability for it. Mine's not going to be perfect. And I want you to draw a dot in the middle. We'll call that the center. And then draw a chord. Make sure your chord does not go through the diameter. It can be any chord that you want. I need you to use the lasso tool and grab that chord and paste it again. Turn it somehow, but don't change the size at all and put it somewhere else. I think you can, right? You just click copy and paste it.
Like without
Don't change the size. Just use there's like a little arrow that's like spinny. Use the spinny arrow thing. Okay. And it doesn't have to look like this. Doesn't have to look like this, okay? It can look like whatever you want, but just make sure there's 2 chords that are the exact same length. Do we all do that? Exactly the same length. That's why I wanted you to use the lasso tool. Are we cool with that? Okay. Since they're the same length, do you agree I can put congruent symbols on them, right? Because we copied the exact same chord. If I were to tell you that there's a piece of the circle that's also congruent to another piece of the circle, what would you guys assume is the same length? Yep, Christian? The minor arcs. Very good. So if these 2 chords are the same length, do you agree those 2 arcs should be the same length? Because it's kind of like, wouldn't this piece, if this is the same length as this piece down here, right? then these should be the same. Wow, that was a terrible drawing. But you guys get what I'm talking about, right? And that's what the first theorem that we're learning today. If we have two chords that are the same length, you guys already could kind of assume that these two arcs, right, that we just created would be the same measure, okay? As long as we're dealing with the same circle. All right, so check it out. The very first theorem that we learned is called the congruent corresponding chords theorem, and we just walked through it, okay? It says in the same circle. Do you guys see that? The same circle or in a congruent circle. How do we know if our circles are congruent?
They have the same center.
No, that's
Oh.
concentric.
Their diameters are the same.
Diameters or their radius, okay? Either their diameter or their radius is the same. Because if their diameter or their radius was the same, would they be the same size? Yes, and all circles are the same shape, right? Okay, so two minor arcs are congruent if and only if their corresponding chords are congruent, okay? So if the chords BA and CD, if those are the same length, right? They're the exact same measure, then the arcs that they create, which are CD and BA, must also be the same measure. Yes?
Is there any converse in this chapter?
There is. Okay? Now, what would the converse of this theorem be?
Ooh.
Yep.
If the arcs are congruent, then the chords are congruent.
Very good. So if the arcs were congruent, right, then the chords that they are formed by must also be congruent. Does that make sense, guys?
Yeah.
This one's really easy converse. Now, this one doesn't necessarily have a converse because this is a biconditional, right? It says if and only if. So it works both ways no matter what, okay? So regardless of whether you're starting with the arcs or starting with the chords, you're going to use the congruent corresponding chords theorem. Make sense? All right. And then we just answer that. How do we know whether two chords are congruent?
Wait, what?
Oh, yes, they have to be in the same circle. What else?
The two lines.
What about it?
The congruence marks, they have to be the same.
Yeah, but how do we know if their chords are congruent?
If they're minor.
The arcs, if the minor arcs are congruent, okay?
Oh, okay.
The minor arcs, you said it before. The minor arcs must be congruent. Cool beans? All right. Oh, whoop. Perpendicular chord bisector theorem. So we're still dealing with chords, okay? This one is very, very specific, okay? So it says, if a diameter, highlight diameter, because it must be a diameter, of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc, okay? I know, that's a lot, okay? So, if a diameter of a circle is perpendicular to a chord, any chord, then the diameter bisects the chord and its arc. So check it out. In this figure, okay, what would be the diameter? EG. So highlight it using that same color that you highlighted diameter with, okay? So what this theorem says is, if it says if EG, if it's perpendicular to our chord, where's our chord here? Which length is our chord? Zoe? FD. Do you guys see that? FD is our chord. If it's perpendicular to our chord, a bunch of symmetry happens, okay? FH, oops, draw these congruence marks. FH is going to be the same length as what? HD. It gets bisected, okay? Also, the arc, FD, is bisected by the diameter. So the arc FG, this arc, is also going to be the same length as what? GD, okay? Now, don't get confused though. That blue line must be a diameter or a radius. You guys cool with that? It cannot be another chord. Do you guys get that?
Yeah.
Because watch, I want you to draw another picture, okay? So if we drew another picture, right? And let's have a chord here. And let's have another chord that goes like this. Do you see how it doesn't go through our center? Okay, this is an example. I want you to put an X next to it because 1 has to be a diameter. Okay? It won't apply if neither is a diameter. Yes, Christian.
I'm just making sure.
Yep.
Chords can be diameters, right?
Chords can be diameters.
Like
They can, yes. But not all diameters are chords. Wait, no. Chords can be diameters. All diameters are chords. Yes. Yeah, Emma?
So, if, like, going off of this, does that mean that the other arcs are congruent, like E, F, and ED?
Ah, yes.
If it's perpendicular, then like the right angle goes on the other side.
You're absolutely right because this is a semicircle, right? So this would technically be 180 minus whatever FG is as an arc. Do you agree?
Yeah.
And then this would also be 180 minus whatever ED is as an arc. And if they're the same, right, then these two are congruent.
So like,
I love that.
what's the point of this theorem? Like, it gives you like a perpendicular angle?
Yeah, so if you're ever given a perpendicular angle and what's formed is from a diameter, right, to a chord, then you have symmetry because of that. It bisects the chord and it bisects the arc created by the chord. Okay? Any other questions? I love our input here. Perpendicular chord, bisector, converse. So if one chord is a perpendicular bisector of another chord, then the first chord is a diameter. So let's say we didn't know it was a diameter, right? If we know that TP and PR are the same length, then this SQ has to go through the center. As long as it's perpendicular and it bisects it, then it has to go through the center, okay? So I want you to draw that dot in there and put that this has to be the center, okay? So we know that SQ has to be a diameter as long as the other two properties are satisfied. So before, with the regular theorem, right? It told us that we had congruent segments and congruent arcs. Now, we were proving that it's a diameter. So if you're given it's a diameter, it's going to be the regular theorem. If you're given that it's bisected, the chord is bisected, and you're proving the diameter, then it's going to be the converse, okay? So whatever you're proving, if that's reversed, you're going to use the converse. Got it? Okay. And then there's one more theorem. Last one, I promise. There's 4 in total, okay? Equidistant chords theorem, okay? So remember how we talked if two chords were the same length, right? Then their arcs would be the same length. Their arcs would be the same measure. In this case, in the same circle or in congruent circles, if two chords are congruent, if and only if, they're the same distance from the center.
So if they're not the same distance, they're not congruent?
Correct. Okay? So, in this theorem, just like in the first theorem, right? We're given two chords, CD and AB, and they're the same length, okay? So we can draw congruence marks on both of them, right? If these two chords are the same length, then their distance from the center must be the same, okay? So FE needs to be the same length as what? EG, okay? Now, you know the distance between a point and a line has to be perpendicular. Do you guys remember that? That's why those 90-degree angles are needed there, okay? Now, one common mistake is students will say EG is a radius. Why is EG not a radius? Stephanie? It doesn't go to the edge of the circle, okay? So please write that down and put like a highlighted X over it. Don't fall for that trap, okay? A lot of students will see it going from the center and it'll go to the chord and they'll think, oh, that's my radius. But it's not, because in order to be the radius, it has to go to the edge of the circle, right? So draw a different line from E to D. Is that a radius? Yes. Do you guys see the difference there?
So wait, what are those lines? Like, what is it called?
It's just, we would say EG is the distance to the chord CD. Okay? And we would say FE is the distance to which chord? AB. Do you guys see that?
Yeah.
Okay? Because remember, the distance from a point to a line has to form that 90-degree angle. Okay? It needs to be perpendicular. This is a lot, guys, but once you see it implemented in a few examples, stuff will start to click. Okay?
You're like, I'm on the verge of breaking.
Okay. One example at a time. Find the value of x and y.
So first, like, it's a
What?
Okay.
We're starting off with this.
So hold on. Let's identify, is anything that we're given a diameter?
yes.
Yes. Okay, so let's highlight our diameter. Do you guys agree that this is our diameter? I mean, technically it's a little bit off because when I print these, I don't know. For some reason, the PowerPoint doesn't like completely convert. But let's assume that's a diameter, right? Does it form a 90-degree angle with a chord? Yes. Do you guys see how it forms this 90-degree angle with the chord? What do we know if that's the case?
They're congruent.
Very good. So let's draw two congruence marks saying that these two are the same length, right?
Did you just make a triangle inside a circle?
Yeah. So watch.
Is that allowed?
This 13, guys, this is supposed to be right there. Just FYI.
So this is gonna be a squared, bro, but like, how does that find a whole circle?
A squared plus B squared equals C squared. So we know that this is 5. This is 13. Can that help us find x?
Yes.
Very good. So what is my C in this case? Xavier? 13. So we're going to say 13 squared is equal to
I get it.
5 squared plus x squared.
5 squared plus x squared.
Wow, that's actually insane.
What's 13 squared, guys?
169.
169?
Yeah.
169 equals, we should know 25 squared is 20, or 5 squared is 25 plus x squared. What do we do to solve for x?
Subtract 20.
Subtract 25. What do we get? 144 equals x squared. What do I do from here? Take the square root of both sides, and we're going to get x equals 12. All right, so we found 12.
And then why is this?
What is y then? Why? It's congruent.
Wait, why couldn't it be? Oh, it's the same thing. Okay.
You got it?
Yeah.
What?
Congruent.
So, yeah, this is 90. What's congruent?
The two
AB.
The two pieces of the chord and the two pieces of the arc. Do you guys remember that? Now, check it out. Do we know what this arc is right here?
Not yet.
Oh,
Yes.
the, 180.
No.
Well,
It's not a
90.
semicircle. Chord.
No, it wouldn't.
I think I know.
Because 90 is close.
Remember, what defines the measure of an arc?
90.
What defines the measure of an arc?
The inside angle.
The central angle. What's the angle that forms this arc?
Oh, 60.
60 degrees.
How did you get
How did I get that?
What?
Do you agree that this is 60?
Who?
Then,
What's that have to do with that one?
what do you mean?
It is
Do you see how this
39.
arc is formed by this angle? If you extend this 60 out, doesn't it form that arc?
Oh.
Yeah.
So this is also 60 degrees.
I thought you were
And
saying
so
the
it's
90s.
died.
I thought you were saying the 90s would
Yeah, I
make
thought it
it
was
the.
the
No.
I'm, I'm very lost. I'm like, just kidding.
Now, this other side is the same, so it also has to be 60 degrees. So together, the entire arc is
120.
120 degrees.
Okay, well, when you look at it like that.
Yeah.
So you don't have to
I
do
guess.
69 different.
We are going to have to find x and y, okay? But the measure of AB was 120 degrees.
See, like, these type of problems are really time consuming.
So, what we do from here, right, is now we're looking for x and y, right? We found what the arc was, okay? But now we need to look for x and y. We know that that angle is 60. The angle, it has a right angle. What does the third angle have to be?
Where?
The angle at point A. It has to be 30 degrees, okay? So now we've got a 30, 60, 90, right? Do you agree that we can write 30, 60, 90? What goes underneath the 30? A. What goes underneath the 60?
A square root
A times the square root of 3. What goes underneath the 90?
2.
2a. And in our diagram, x is the side opposite the 60. Y is the side opposite the 30. And what is opposite the 90? 6. So if 6 is equal to 2a, what is a? 3. So a needs to be equal to 3. So what would x be?
X is 3 square root of 3.
3 times the square root of 3, which when you plug it into your calculator and you round to the tenth, 5.2. And then y is 3.
So,
I have a question.
Yes.
In this kind of problem, oh no, because it's 30, 60, 90. But if it wasn't 30, 60, 90 and you had one of the like degrees inside and it was a right triangle,
Yeah.
can you do like sine, cosine?
You could use sine and cosine here, yeah.
Oh, you
Absolutely.
can't use it
Yeah,
here?
you could. So how would we set it up? We would say the sine of 60 is what?
Is
SOHCAHTOA, right?
opposite, so x over 6.
Good. And you would get x is equal to 6 times the sine of 60 degrees. And I guarantee you're going to get 5.2. Did you get it?
Yeah.
Yeah. Cool, right? And then the cosine of 60, right, would be y over 6. And then the cosine of 60 times 6, I guarantee will give you 3. Okay? All right.
oh, I know how to do this one.
So, this one. Guys, are the segments that they're giving us, are those radii?
No.
No, they are not, okay? So, this is actually giving us what? What are we looking at here? Chords, 2 chords. And what are the 90 degrees mean? What does that mean, Gabby? They're perpendicular to the chord, so it's telling us what, Christian? Why do they need to be congruent?
Because they're the same distance from the
The chords are the same distance from the center. Do you guys agree with that? Because the fact that it told us that these are the same length, right? We know, because Christian's super smart, that these have to be the same length. The chords are the same length. Are we cool with that?
Yeah.
So, if this side, if we continued this line out to the side, right? Does this become a radius?
Yeah.
So is this radius technically perpendicular to our chord?
Yeah.
That means it does what to our chord?
Bisect.
Bisects it. So what does x have to be? 8. And then if y is the same distance as the other chord, what is the distance of y? 16, because you add them both together. Cool, right?
See, I feel like I wouldn't be able to figure this out if you weren't.
That's why we practice. Jaden, what's up? Yes. Two, find the measure of the arc CD in the diagram, okay? So let's take it one piece at a time. What are we looking at here? Start defining some stuff.
Oh.
Yeah,
A radius.
very good. From A to D. Excellent. So A to D is a radius. And what would B to D be? Diameter. Very good. So we've got a radius. What else do we have? Mariana? A chord. Excellent. C to E is a chord. What's going on with our radius and our chord, Emma?
AD bisects CE.
Very good. Why?
Because it's perpendicular.
Because it's perpendicular. So we know that this has to be the same length as this. What else do we know?
Oh! Sorry.
Mariana?
BA is also a radius.
BA is also a radius. Yep. Yep.
Arc CD is congruent to DE.
Very good. The arcs are also the same length. Do we see that? Okay. So you see how we started from nothing and we just took it piece by piece and we were able to come up with what we needed to know? So if those two are the same, if they're congruent, they're the same measure, what do I do with them?
Set them equal.
You equal them, okay? So we're going to say 9x is the same as 80 minus x. And please write one more thing. It's because the arc CD is the same as the arc DE, okay? They're congruent. Yes? All right, so now how do I solve this? Christian?
You do like 9x equals 80 minus x. And then you add x to the other side.
Good.
You get 10x equals 80. Divide. You go to x equals 8. And then you multiply 8 times 9. You get 70.
Excellent. So it's asking us for the measure of the arc, right? Not just for x. So in order to find the arc CD, right, we need to plug it back in, and we'll get 9 times 8, which will give us 72 degrees. Yes? That was
About
a
80
fun
minus
one.
at
You could do that as well. You could do 80 minus 8, and you would get 72. Okay? Because they have to be the same length, right? So that's actually a really good way to check to make sure that you got the right x value. Okay? Questions on this one? All right, good work, guys. Let's take a look at the last one. Example 3. In the diagram of circle C, QR equals ST, which is equal to 16. Let's find CU. Emma?
You set 2x equal to 5x minus 9. Because equidistant
From what?
from the center in the chord.
Very good. How do we know that C or QR and ST, those two chords, have to be the same distance from the middle? Why do they have to be the same distance from the middle? Anna? They are perpendicular to those lines, but why do they have to be the same distance? Go ahead, Anna. Try again. What do we know about those two chords? They're congruent. And if two chords are congruent, remember, they have to be the same distance from the middle. So this has to be congruent to this, just like Emma said. So CU, it's not an arc, it's a segment, must be congruent to CV. Therefore, we set 2x equal to 5x minus 9. Someone solve this for me. Mariana?
Track back on this.
Mm-hmm.
Yeah, -3x, and then you divide -3 to both sides,
Mm-hmm.
and you get just 3.
X equals 3, right? Is that the distance of CU, 3? No. Plug it in. Okay, so you plug it back in. You're going to get CU equals 2x, and you get CU equals 6.
Wow. Math is just like.
Hold on. Hold on.
More?
I want to add more. What if I asked you to find the radius of the circle?
But isn't there no radius?
There's no radius drawn here.
Oh, would you have to find a diameter, then cut it in half?
We could.
How do you
Yeah.
Do you agree? Would CQ be a radius?
Oh my literal
Gosh, and
gosh.
you have two sides.
I love how you
Oh, we have two sides of what?
A triangle.
Of a triangle. Because CU is what? What's the distance here? 6, right?
Oh my.
But do we know what QU is? It's 8, because it's divided in half, right?
Oh my gosh.
So how could we figure out the radius?
Math.
Yeah, well, of course we use math.
Pythagorean.
The Pythagorean theorem. We know two sides of a right triangle, so we're going to say 6 squared plus 8 squared equals our radius squared. Ugh, that was gross. Okay? And then what's 6 squared? 36. What's 8 squared?
64.
64. And then we have our radius squared. What's 36 plus 64? It's 100. What's the square root of 100?
10.
So our radius is?
Oh my
How cool is
That
that?
is absolutely insane.
And that's all I want you guys to do today. All right? So once you're done with this one, you can turn them in.